Welcome back. I'm Erin. This video is part 2 of a series introducing the idea of pre-training for the lasso and sharing its associated software package PT Lasso in R. I'm excited to take a deeper dive into lasso pre-training with you and to look at more examples. Now before we jump in, I want to start by thanking my collaborators on this project listed here. As a reminder, part 1 of the series presented an introduction to pre-training for the lasso. We considered an example of input group data. We imagined a data set spanning 10 cancers where our goal was to fit a lasso logistic regression model to predict 10 years survival. Lasso pre-training allows us to identify features that are predictive across all cancers, as well as features that are predictive in just one cancer class. We then showed how to fit pre-trained lasso models using the R package PT Lasso. In this video, we'll show how to do lasso pre-training for 3 more settings: target group data, or data with a multinomial response, multi-response data with Gaussian responses, and multi-response data with time-ordered responses, or time series data. Here is what model fitting with PT Lasso looks like. As before, we'll fit models using PT Lasso or cv.ptlasso for cross-validation. We pass in our data X and Y, as well as the use case or modeling setting. This will be target groups, multi-response, or time series. Then we plot with the function plot, predict with predict, and extract coefficients with the coef function. First, we'll start with target grouped data. And by this, I mean data with a multinomial response and no other grouping on our observations. In the target group setting, the response we wish to predict is in one of 3 or more categories. One such example is the iris dataset. We have measurements of irises, and we want to predict to which category each iris belongs: setosa, versicolor, or virginica. The pre-training philosophy here is analogous to that for input groups. We want to learn features that are predictive for all 3 classes, and we want to learn features that are specific to each individual class. As in the input groups case, lasso pre-training again happens in 2 steps. In the first step, we fit a lasso penalized multinomial model using a group lasso penalty on the coefficients. Now recall that the multinomial logistic regression model is a collection of one versus rest models. The group lasso penalty forces these models to use the same features, but each of the classes can have different coefficient values. This step identifies features which are predictive across all classes. Now in the second step, we fit separate one versus rest models for each group, where the fitting is guided by the overall model from step 1. And as in the input group setting, we use a hyperparameter alpha between 0 and 1, together with a penalty factor and offset defined by the overall model. More details are in part 1 of this series and in the PT Lasso vignette. Now importantly, when alpha is 0, this fits a fine-tuned version of the overall model for each group. That is, the pre-trained models can only use features that were selected by the overall model, and it uses the full prediction from the overall model as an offset. And at the other extreme, when alpha is 1, this approach completely ignores the overall model and fits a separate one versus rest model for each group. Now let's look at an example of how to fit a model for target grouped data using the PT Lasso package. Suppose we have a simulated data set with a multinomial outcome. We want to predict whether each observation is in group 1, 2, or 3. Our toy data set has 900 observations and 100 features. 15 features are predictive across all 3 classes, and each class additionally has 10 class-specific features. The simulation code for this dataset is in the R Markdown file that accompanies these slides. Here is how we fit a model with PT Lasso. We call the PT Lasso function with our data X and Y, and we specify the use case is target groups. Now recall that pre-training for the lasso uses a hyperparameter alpha. Here we choose alpha equals 0.5. This is chosen at random and is just for illustration. Under the hood, PT Lasso uses cv.glimnet from the glimnet package in R to fit lasso models. As a result, we may choose to specify the performance metric that Glimna uses for model selection. Here, I've specified that our type measure is class, or the misclassification rate. Now in our setting, PT Lasso trained 7 models. We have 1 overall multinomial model using all 3 groups, 3 pre-trained 1 versus rest models, and 3 individual 1 versus rest models. A call to plot shows the cross-validation curves for each of these models. To make predictions for new data, say X test, we simply pass it in to our call to predict. This will make predictions for all 7 models. Now by default, PT Lasso uses lambda min, the value of the regularization parameter lambda that minimized the cross-validated error rate for each Lasso model. But if you'd like to use a different value, you can specify this in your call to predict. If you also provide y-test for model validation, predict will return performance measures. Our performance metrics include the overall misclassification rate, computed by treating this as a multinomial problem, and the mean and group-specific misclassification rates, computed by treating this as a set of 1 versus rest problems. Now to combine the 1 versus rest models to a single multinomial model, we assign observations to the class with the highest probability from the set of models. Now on the bottom of the slide, we also show the support size, that is how many features were selected for each model. With PT Lasso, we can easily inspect model coefficients. The function coef returns a list with the coefficients for each of our 7 models. And as with predict, it uses lambda.min, but other choices of lambda can be specified. The pre-trained coefficients, for example, will be itself a list of length 3 containing the coefficients for each of the 3 groups. Now initially, we chose the pre-training hyperparameter alpha equals 0.5 at random. But of course, we recommend making a more careful choice in practice. With PT Lasso, we can use cross-validation to choose alpha. The plot on the left shows the cross-validated misclassification rate if we treat this as a multinomial problem. And the plot on the right shows the sum of cross-validated misclassification rates that we would get if we treated this as a set of 3 separate problems. And of course, we can predict with new data using our cross-validated model. By default, predict will use the value of alpha that minimized the cross-validated error. Here, we see that it used alpha equals 0.9. But if you'd like to use a different value of alpha, you can specify this in your call to predict. And that's it for target group data. We know how to fit models with or without cross-validation to choose alpha, how to plot them, how to make predictions, and how to extract coefficients. We'll continue now to look at multi-response data and time-ordered multi-response data. But before we move on, I want to point out that we now know the general framework for lasso pre-training. The examples to come will be very similar to what we've seen so far. Likewise, we also know the general framework for using PT Lasso. The function calls in the remainder of this video will feel very familiar. Now, let's look at how to use pre-training for multi-response data. Multi-response data has multiple responses for each observation. For example, data like this may come from a survey where each person answered multiple questions. In this case, the people would be the observations, and their answers to the questions would be the responses. PT Lasso supports the special case where all of these responses are continuous. The pre-training philosophy here is analogous to that for input groups and target groups. We want to learn features that are predictive for all responses, and we want to learn features that are specific to each individual response. Again, lasso pre-training happens in 2 steps. In the first step, we fit a lasso penalized multi-response model using a group lasso penalty on the coefficients. This step forces all responses to use the same features for prediction. And in the second step, we fit separate linear regression models for each response, where fitting is guided by the overall model in step 1 and the pre-training hyperparameter alpha. Now, as before, when alpha is 0, this fits a fine-tuned version of the overall model for each response. And at the other extreme, when alpha is 1, this approach completely ignores the overall model and instead fits a separate model for each response. Let's walk through an example of how to fit a model for multi-response data using the PT Lasso package. Here we have a simulated dataset with 2 Gaussian responses. The first 5 features are predictive for both responses, and there's an extra set of 5 features that are predictive for each response. We have 650 observations and 500 features total. Now we have our data and we're ready for model fitting. We'll again call PT Lasso with our data X and Y, and now we specify that our use case is multi-response. As before, we'll use the pre-training hyperparameter alpha equals 0.5. Now PT Lasso uses cv.glimnet to fit 5 models. It fit 1 overall multi-response model for both responses, and then 2 pre-trained models, 1 for each response, and 2 individual models. And as before, we can plot the cross-validation curves for each of these models. To make predictions for new data, X-test, we just pass it in to our call to predict, and PT Lasso will make predictions using all 5 models. If we also provide Y-test for model validation, predict again returns performance measures. Our performance metrics here include the overall mean squared error, or the sum of the mean squared errors for both responses, the average mean squared error across the 2 responses, and then the mean squared error for each response. And COEF again returns a list with the coefficients for each of our 5 models. The pre-trained coefficients are a list of length 2, containing the coefficients for both of the responses. Performing cross-validation to choose alpha is the same as before. We call cv.ptlasso, but now specify the use case multi-response. Plotting this call shows the cross-validated mean squared error as a function of alpha. And note that the mean squared error here is the sum of mean squared errors across the 2 responses. We can again predict using our cross-validated model. Here, we call predict with X-test and Y-test for model validation, and it returns performance metrics in addition to the predictions. And that's it for multi-response data. Our last example will be time-ordered multi-response data. Time-ordered multi-response data is similar to our previous example. We again have multiple responses for each observation, but now these responses are measurements of the same outcome at different time points. This often happens in medical settings where we observe patients across hospital visits and measure the same biomarker at each visit. In this case, the biomarker measurements would be the responses. We can fit pre-trained lasso models in this setting using PT Lasso when the responses are all Gaussian or all binomial. PT Lasso also supports the setting where the features X are remeasured at each time point. The pre-training philosophy here is not much different than what we've already seen. We want to learn features that are predictive across responses, and we want to learn features that are specific to each individual response. Only now we take time ordering into account. Our intuition is that the relationship between our features X and responses Y likely changes across time, but those relationships are certainly related. So here, lasso pre-training happens in a series of steps. In the first step, we fit a lasso penalized model for the first time point. And in the second step, we fit a model for the second time point, guided by the model from the first. And then we would continue on this way. We would fit a model for time 3, guided by the models from times 1 and 2, and so on. Let's look at an example using PT Lasso. Here we have a simulated data set with 2 Gaussian responses ordered by time. We have 300 observations and 100 features. The first 10 features are predictive for both responses, and there's an extra set of 5 features that are predictive for the second response. To fit our pre-trained models, we'll call PT Lasso with X and Y, and we'll specify that our use case is time series. Now PT Lasso fits 4 models. There are 2 pre-trained models, 1 for each time point, and 2 individual models. And as before, we can plot the cross-validation curves for each of these models. And with a call to predict, PT Lasso will again make predictions using all 4 models. And if we provide Y-test to our call to predict, then predict will additionally return performance measures. Here, our performance metrics include the average mean squared error across the two responses, as well as the mean squared error for each response. We extract coefficients using the coef function, and coef will return a list with the coefficients for each of our 4 models. The pre-trained coefficients themselves are a list of length 2 containing the coefficients for both responses. As we've seen before, we can choose the pre-training hyperparameter alpha with cross-validation using cv.ptlasso. And plotting this object will show us the average mean squared error across both responses as a function of alpha. And we can predict with our cross-validated model. Passing in y-test tells the predict function to compute the additional performance metrics. Before we wrap up, there's one more detail I want to share for pre-training with time series data. We just did an example of pre-training where y had repeated measurements, but it may be the case that the features x are repeatedly measured as well. Ptlasso supports this case. Just pass in a list for x with one entry for each time point. And you can see an example of this in the Ptlasso vignette. Thank you for watching this deeper dive into lasso pre-training. Now we know how to do pre-training for all of the settings that Ptlasso supports: input groups, target groups or multinomial response data, multi-response Gaussian data, and time-ordered Gaussian or binomial data. The vignette for the Ptlasso package contains examples for all of these cases and many more, including settings that are not supported by Ptlasso, like conditional average treatment effect estimation and multi-response data with different response types. Below, I'll include links to the Ptlasso package as well as the R Markdown package that accompanies these slides. Thank you again for watching, and I hope that lasso pre-training is helpful to you.